Hey, everybody.
Have you ever noticed how hard it is to locate a sound coming from an app or a game? It might even sound flat. My name's Steven Wilsons.
I'm Adam Tuliper.
And during this session, we'll show you how you can use spatial audio to accurately put a sound in a three-dimensional space. And you'll be able to do that on HoloLens, Xbox One, Windows Desktop, and Windows Phone. So what is spatial audio? Traditionally, audio has been flat, whether that was headphones, 5.1 speaker configurations, 7.1 speaker configurations. But now spatial audio gives you the illusion that a sound is coming from a particular location in a three-dimensional space. If you hear a sound coming from an application as if you would from real life, that really is spatial audio done well. At Build, we're announcing Project Penrose. And with Penrose, we've exposed Microsoft's HoloLens audio technologies to UWP apps and games. And again, you can do this on HoloLens, desktop, phone, and Xbox One. This technology uses HRTFs, and as such is optimized to work well with headphones. As a developer, you'll see how you can now enable spatial audio through the Audiograph API or Unity. As I mentioned before, to experience spatial audio with Penrose, you'll need headphones. The speakers you have in this room will only give you a hint at what spatial audio can really do for you. You can try the HoloLens Academy. Many of you have tried before. You can download the code we'll show you for the demos, and you also can download the games afterwards. You can also come and find us to see hear some of these demos in person. So what are HRTFs? HRTF stands for Head-Related Transfer Function. And with our 2 ears, we can hear sound in 3 dimensions. One is direction, so I can hear whether a sound's coming from the left or the right of me. I can hear whether a sound's coming from front of me or back of me. I can distinguish elevation, and I can also estimate the distance from where a sound is coming. Your head shape, your external ears, your internal ears, and your brain will work together so that you can perceive location accurately. An HRTF will describe how a sound would reach your ears, your left and your right ears, when it's coming from a location in space. So when you actually record a sound at a certain location, when you move away from that, an HRTF will describe the transfer that happens to the sound. And you will get the illusion that the sound was actually coming from where I just pointed at. Head orientation tracking is really important to improve accuracy of sound localization. And as you can move your head, you'll notice that it greatly reduces from back confusion, and it improves elevation perception. We'll show you a demo in a couple of minutes of how you can use one of the headphones that are available in the market today to implement head orientation tracking and just greatly improve that accuracy for you. In Windows 10, we introduced the Audiograph API. So the Audiograph API has a bunch of input nodes on one end, a device input node where you can connect a device like a microphone to, a file input node you can load a WAV file or an MP3 file with, or an audio frame input node if you were already processing audio or video in the Windows stack. You can apply effects to them, or you can submix them. And once you're done submixing them or applying effects to them, you can output them to a device, a speaker, for example, a file, or you can continue processing them in the Windows stack using the audio frame output node. Now in Windows 10 Redstone, we are adding emitters and listeners. What is an emitter? An emitter really is the source of spatial audio. It's where the sound is coming from. An emitter can either be an input source or a submix. The number of emitters that we support really depend on a number of factors in your application. One is how much CPU do you want to sacrifice, how much CPU does your device have, or computing power does your device have, and does your device support hardware offload or not. An emitter can have an orientation, it can have a position in space, and it can actually travel at a velocity. On the other end of sound, there's the listener. And that's where we perceive sound. We only support one listener at the current time per audio graph, and a listener itself can have an orientation. It can have a position in space as well, and it can also travel at a velocity. So let's have a look at that original graph. So now you'll see all of our input nodes can now have an emitter, and a submix can have an emitter as well. And on the right-hand side, you'll see that our device output node now has a default audio node listener object for which that you can use to configure where sound is perceived. All right, let's have a look at a first Hello World demo and call that Hello Spatial Audio. Before we do that, before we actually show you the demo itself, let me show you the graph we built. The graph is very simple here. We're loading one file input node with the siren of a car. We're positioning it in space by adding an emitter to it. And we're sending that spatialized sound that you'll get, we're sending that directly to our device output node. The reason we're doing this is that it'll support hardware offload in the future. We're also adding a reverb path with reduced gain, and we're sending that to the submix node where we actually are applying the reverb, and as well sending that to the device output node. The code to do this is very simple. First off, we're creating an audio graph. We're setting the audio category, which is game effect, so that the proper ducking policies are put in place. We're also making sure that we configure our output correctly, setting it to 48 kilohertz, setting it to stereo for our headphones, and 16-bit float. And then we're creating our graph. And if our graph creation is successful, we'll continue. Now, our graph is really built from the output nodes to the input nodes. So the first thing we'll do is we'll create our device output node. We'll create our device output node saying, on our audio graph, create device output node async. And once that's successful, our next step happens, and we keep building our graph. We're adding the reverb submix node. We're creating a submix node, and we're adding it to our output node. We are also reducing the gain for that. And finally, for our reverb, we're adding the reverb effect, we're creating it, and we're adding it to the submix. Now, our next step is to create that emitter. That's really where the sound will be coming from. We're creating an audio node emitter. We're giving it a omnidirectional emitter shape, which means that the sound will go in every direction. We can also create a cone, for example, where you will only hear the sound as long as you're in the projected cone. And we're positioning our emitter. And we're using a right-hand coordinate system for that. So negative x is left, a positive 1 is right, and then we have y and z. And z is, surprisingly for some people, negative in the front and positive in the back. Our next step is, now that we have our emitter, we're loading our file. Currently, for spatialization to happen, all of the sound you attach with an emitter needs to be mono and encoded in 48 kilohertz. So we're loading a mono 48 kilohertz car siren. And once we've done that, we're adding it, we're creating the file input node, and we're passing the emitter in. So at this point, we have our file input node, and we positioned it in space by adding our emitter to it. Once we've successfully created our emitter, we're adding it to our submix, and we're adding it to our output node. And at this point, our graph's been completed, and we can show you the demo. What's very neat with this simple demo, and you'll be able to download the code afterwards, is that we have a car here, and the car's positioned away from you, so the sound will be less loud. As I drag the car, we'll update the emitter position. We'll also add velocity to the object, which will create a Doppler effect. So let me give it a try. Very simple demo to add an emitter to your audio graph.
I'm going to wake up with that sound in my head.
Oh, yeah. Well, we've gone through a couple of dry runs. The next step is, how do you add head tracking to your audio graph? So what we did for that is we're using the Jabra Intelligent Headset, which provides us with an accelerometer, a compass, a magnetometer, GPS, etc. And we're using that one to update our listener orientation in the next demo. So from a graph perspective, what we're just doing is we will build the same graph. The UI will look a little bit different, but we'll start updating our audio node listener object. So the first thing we're doing is from this headset, we'll read yaw, pitch, and roll as a coordinate, as a vector 3 coordinate, x, y, z coordinates again. Our next step will be to convert the angles we'll get, the Euler angles, to radial angles. Formula is right there. It's just a simple math conversion. Then the next step is to make sure that our orientation is set as part of a quaternion. Quaternion is oftentimes used in the game development world to avoid gimbal lock. It's a pretty well-known problem there where two axes collide and you can't just move one coordinate anymore to make sure your object turns. All right, let's have a quick look at that demo. You'll see it's a spatial sphere demo, and I also I did a recorded session where I'll go step by step to the code to actually make this demo happen. So what I'll do in...
I think switch over.
Oh yeah, let me switch. In this presentation, you'll see a sphere, and if you let the demo run, I'll position a ball and a sound around you, and you'll hear the sound move. It'll work a lot better with headphones, as I mentioned before. What will also happen is that as I move my head, you'll see my little bobblehead move along with me, and it'll update the position of sound. Hopefully.
Front position. Front right position. Right position.
So as I move my head now,
Right position.
for me, the sound is moving with me.
Position. Right position.
I think it's a pretty cool demo
Right
and
position.
how to show how you can use head orientation tracking to just make sure you have a more realistic experience of audio. And if you're just playing a game or something, just those small movements will help you locate the sound a lot easier. All right, now that we've seen some of the simple introductions on how to use spatial audio, let's talk about what are some real-life applications you can have. First one is augmented and virtual reality. It's very simple. You've all seen it. It's a must-have to create a realistic perception. If you're creating great audio, or if you don't create great audio in a virtual reality, it is easy for your users to really just snap out of that experience and it doesn't work well for them. Another experience you can create is watching movies. So as you have surround sound, what you could do with this technology is virtually position the speakers around your head. So you can take surround sound input and actually listen to a surround sound experience with headphones. Another experience you could build, for example, is a music experience, where if you use this technology, you'll notice that the sound actually is more externalized, and it just creates a more, I think it's just a better listening experience for the audio scene. What we've also experimented with was just positioning all the different instruments in a different location, and you get a very interesting perception of sound that way. And then there's gaming. Now, how neat is it if you play a 3D shooter and you hear somebody sneak up behind you? You can just turn around and shoot them. You know that the sound will be coming from behind you. At that point, you just became a better gamer, and we just raised the bar for gaming. One of the applications of augmented reality does not have any visuals with it. It's the GuideDocs project we've been working on. And with the GuideDocs project, we're helping people that are visually impaired to navigate through the world more comfortably with the use of spatial audio. So as they're walking around, we are tracking their location, And we're making sure that as they're, for example, walking by a coffee shop, we give them an indication that there is a coffee shop. But we don't have to say things like, there is a coffee shop 30 degrees from you at about 15 meters. Just by saying there is a coffee shop and positioning the sound, they will be able to locate where that shop is, and we just don't interfere as much with their daily experience by having all that text be thrown at them. Some of the key technologies that are being used here are spatial audio, but also background audio, which has become a lot simpler in the new version of Windows 10, and we'll talk about that. You've seen the headset that we've been using through Bluetooth, and it also uses Microsoft mapping services. I mentioned virtual speakers before, and we'll build a demo here using Big Bug Bunny, which is my favorite video of all time. This one's a little bit more complicated, this graph. So what we're doing is we're taking a video file with 5.1 speaker audio. We're passing that to a media clip, which is a media composition class. And to that clip, we're adding the spatial audio effect. So what we'll be doing here is that we'll get an audio frame in this spatial audio effect, and we'll take the 6 channels, we'll split them up, and we'll position them in different audio frame input nodes, and we'll put them around my head. That's pretty much what the graph will look like. It's a graph you're fairly familiar with at this point. So as I mentioned, you have the audio frame input node, you add an emitter to it, and you send it to an audio frame output node instead of a device this time, so that you can loop the result, the spatialized stereo version of the sound, back to the effect, replace the original audio, the 5.1 audio, send it back to the media clip, to the media element, and hear it through your speakers. So how cool is that? All of a sudden, I got a 5.1 surround system just using my headphones. So the code here is fairly simple, and it's creating the media clip first. I'm loading my file, and then to the audio effect definitions, I'm adding my spatial audio effect. Now, the meat of the code is obviously in the spatial audio effect, and we'll share that code out after this presentation. Our next step is to create a media composition object and add our clip to it, and then just set it as a source for the player. Let's have a look at that demo. So as this video plays, what you'll notice is that as sound's playing throughout the video, different speakers here in this will light up as they're receiving volume. So you've now created a much richer listening experience for people with headphones. Very simple. One of the things you noticed is that as soon as I minimized my application, it stopped playing, which is not great for video, but it definitely is not great for music scenarios. So what we're announcing today as well is a change in how background audio works. And background audio works great with audiograph as well. So what you do now is you add the background media playback capability. And with that new capability, you can now write all of your code in one process versus the 2-process model you had to do before, where in the one process you had your UI, and in the second one you controlled all of your playback, which was very confusing. Now with the one-process model, when your application is put to the background, the XAML textures are unloaded and the memory footprint of your app comes down. The next thing that happens, you get a notification saying you're minimized, and you can clean up more resources if needed. And if needed means if you're over a memory limit. If you're actually over the memory limit, you'll get another event, and you will need to clean up your resources, or you will be potentially closed as an application. When you're foregrounded again, and your visibility has changed, you get a notification for that as well, and XAML's rehydrated. So it's very simple. With a couple of notifications, you now implement the background audio in Windows 10 Redstone.
All right, that was pretty awesome. You can take C# and work with the Audiograph API. I think the first time I heard that, it was neat because you were, to really stress that point, you're taking all those multiple channels and making my regular headphones hear it just like I was almost on 5.1.
Absolutely.
All right, so that's one option that Steven showed to be able to work with the Audiograph API. One of my favorite programs of all time outside of Visual Studio is Unity, a very popular gaming engine middleware. And to be able to use our spatial audio API behind the scenes with Unity is actually pretty easy. So we've worked to create a couple neat demos to show you that is going to showcase, I think, some of the audio features and how to do it inside of Unity and some of the cool things that you can do. Now, audio in Unity has a couple different facets to it. You have 2D audio. And traditionally, think of when you're playing a game. A 2D game, it's the easiest use case to look at. The background music to your game is a pretty consistent volume while you're playing your game. Doesn't matter where you go in your game, it plays pretty consistently. It might fade out, it might fade in, but it's not positionally sensitive. The same thing can happen in a 3D game as well. You can have 2D audio in a 3D game. You have a first-person shooter, and you're running around shooting zombies. You got a heavy metal track playing in the background. Also 2D audio in a 3D game. Now next, you have 3D audio. 3D audio, as it stands out of the box, is really, it's a mix between volume control and panning from left to right based on the position of the listener to the various audio sources. So the closer you get to a sound, the louder it's going to be. If you hear a gunshot off to the left-hand side, you're going to hear it out of the left-hand speaker. If you rotate essentially the audio listener, you're going to now hear it out of both speakers pretty evenly, and you get closer, it's going to get louder and louder and louder until you reach a distance where it won't get any louder. Then we have spatialization. You might think that 3D audio is spatialization. There is a difference, though. Again, 3D audio is still, it's pretty much flat and planar. Spatialization, as Steven showed in some of the demos, you can hear things behind you, the police car when it goes behind you. So it's not just panning or volume control. Out of the box, Unity doesn't have spatialization with it, but however, it does have the ability to have a spatialization plugin. So we have an MS HRTF spatialization plugin for Unity. You can also add it to the project, or as was just announced, I believe yesterday, with Unity 5.4 that has HoloLens in preview, that has it out of the box, and future versions of Unity will have this plugin there out of the box. You just need to make sure that you go in and enable spatialization in your project. And you can do that underneath Project Settings Audio, select the particular spatializer that you want to use, and then you're all set to go from the plugin standpoint. Now, you still need to configure a couple other things. But now, what are we doing with this spatialization? Inside Microsoft, we've actually tested over 350 people. We measured the size of their ears, size of their head, and measured actually 96 different biometric pieces of data about each one of those individuals. And we've come up with a pretty standardized head model that fits a good portion of the population out there. We can essentially predict, on top of that, how you're going to hear audio by the way you look. So personalization of these HRTF, head-related transfer functions, is actually being used in the HoloLens currently. And we're going to be bringing this to future versions of Windows as well to be able to use this personalization aspect of HRTF in your other applications. Now, spatialization options. This is important. We've already configured a plugin. We have a next step that we need to do. We can do it manually. And doing it manually, you can spatialize. You've got to go into an audio source. In a Unity project, we typically drop audio sources all over. If there's a waterfall, there's an audio source over there. If there's a zombie, it has an audio source over there, as we'll see shortly. We have a pretty cool zombie demo. And you need to make sure that you check off Spatialize. The important thing to note is if the plugin is not enabled, Spatialize won't show up. Then you choose a spatial blend. It's a little slider to determine whether or not you want 2D or 3D. And there's different use cases for using that. Sometimes, if you get closer to sound, some folks will make it over to 3D side. But for spatialization, you want that all the way over to 3D. You want a 3D sound, spatialized. Now that's if you're going to manually configure it, and you can do this on any of the audio sources in your scene that you want to be spatialized. There's another method that you can use to auto-configure all of this. It requires a little bit of code to enumerate your game objects to do that, and we'll look at that in just a couple slides. But first, let's talk about the plugin parameters and how we can talk to the spatialization plugin. Any spatialization plugin can define their own custom parameters that you can communicate with from inside of Unity. The Microsoft HRTF plugin, we have two main parameters that you communicate with. The first is a room size or room model. If you're in an office, there's a little bit of reverb that's added to the sound in there. And your ear senses that. Now, this is not reverb added for effect. If I'm playing guitar, I might add a reverb effect on there. That is an effect. Sound that you hear in the real world has a little bit of reverb, depending on the room, added to how you hear audio. And so our HRTF functions try to model that to make it so you can hear the sound in a realistic way. So our HRTF code will say, OK, you've specified a small room model. Then we're going to add and integrate a little bit of reverb onto the HRTF this way so it sounds realistic. You have the ability to specify a medium room. In here, I would specify a large room. Or number 4 is you're basically going outdoors where you're going to have an extremely minimal or nil amount of reverb added to that. Next, we have a roll-off, which allows us just some fine-tuning of volume curves. It's a logarithmic curve, and we can essentially say, here's your minimum gain and maximum gain, how we can affect the decibels depending on how close or how far away we get from an audio source. Just some extra abilities to tweak those values. Now, using it in Unity, it's as simple as this. On a particular game object, you add a little bit of code. The first line is common practice across Unity. That's how you get a component, an audio source. We get a reference to our audio source, and then we just simply call set spatializer float. That communicates to the plugin to tell the plugin, in this particular case, value 1 is room size, and then we're going to pass in room size small. That's it. That's how you configure an audio source for spatialization, enabling the plugin, and communicating with the plugin to say, for this audio source, we're going to use a small room size. Now, I mentioned we can also do this automatically. I showed the manual configuration. If we want to auto-configure it, we can use just a little bit of code. And let's assume we have a use case that in a small room, we have 50 different objects we need to spatialize in there. What we can do is we can add a tag. A tag is just some text you assign to an object in Unity. And we can tag all of our particular objects in that small room with the tag spatial emitter small. It's going to be any text you want. I just chose spatial emitter small. And so that line of code enumerates all of those game objects, gives them back to you. Next, you can just write a little bit of code to configure the audio sources for each of those game objects. And then next, you just communicate with those particular plugins. For the spatialization plugin, you say for each of those objects, go ahead and set the room size to small. If you had a medium room size, you could have spatializer emitter medium, spatializer emitter large. And so it gives you just one bit of code that auto-configures everything for you, so you don't have to worry if you missed any options or didn't set them correctly. For this next demo, we worked with a partner, DreamTap, to implement a zombie supermarket. I love zombies. I love zombie shows. So there's a couple considerations. When you're making a game or an experience with spatialized sound, you can't just drop any audio anywhere, because there's things that folks that have been doing game and app development for a while, they might have some expectations, like, oh, let's just throw sound in there. Position becomes extremely important, as we'll see. So let's check out this demo. All right, first, let's go ahead and play it. You'll notice right away there's a zombie sound. Let's actually go ahead and maximize this. Okay, now listen to the audio. We are currently spatialized. As you can see, kind of on the left-hand side of the screen, spatial audio is on. We are in a small room size. Let's change the room size to medium and large.
It's better if you walk into
None. Small. Medium and large. And if we turn it off, you can hear the instant effect. Right? Everything is kind of a consistent volume, almost like you have headphones on, but it's all panning the same way. Now let's turn around here. And we have the scariest zombie of all. We have a zombie that looks frightening like me. Let's off that zombie. Now listen in here. We have a plane overhead. We have some zapping wires. And lastly, we have some speakers in here. As I turn away, right, we can hear the position. The sound is up there. It's coming from up there. It's spatialized. So with these sounds, there's a couple different things. We heard footsteps as we're walking along. So let's look at my character here. If I scroll back, let's talk about two things first that we use to enable this. Edit, project settings, audio, and here we have MS HRTF Spatializer, so we've added the plugin. Now anywhere, when we have an audio source, we've configured our audio sources to have our spatialized settings, and notice we're set to 3D. So our sources are all set up for us. But why do we have so many different options here on our first-person controller? There's 1, 2, 3, 4, 5, 6, 7, 8 different audio sources just on my main character. Why so many sounds for just one character? Well, as we started this and we had something like the footsteps. Footsteps, typically an audio source is about here on a user. When you're playing footsteps from your midsection in a spatialized world, it sounds weird. When you play in a non-spatialized game, it's just kind of what your brain is used to in playing a non-spatialized game. So we took those sounds, we put them on the floor, and they suddenly sounded like they were coming from the floor, as you'd expect. Now overhead, we have one each for rain, so we have a left channel and a right channel for rain. Now our spatialized audio sounds should be mono. So we have slightly different sounds to make sure they're not phasing for left and right, and they're playing overhead. You ever see the old cartoons where the storm cloud follows you around wherever you go? That's exactly what happens here. And the reason that we do that is rain is always overhead. It's positionally placed, and it follows us around wherever we go. We don't need multiple ones set around our scene. If we walk, notice our audio goes with us. We did the same left and right for an airplane. But there's a special case that comes with something like an airplane. When somebody records the sound of an airplane, what do? Do they hang on the edge of an airplane with a microphone? They don't. They're on the ground, they're listening to that airplane, and as such, because of the speed of the airplane, you get Doppler shift. So a sound out of the box that you record of an airplane has Doppler shift associated with it. So that's one of the settings you need to make sure that you turn off. We don't want additional Doppler sound included on sounds, on audio that already has Doppler built in. That was one of the challenges with getting the airplane sound. That also follows us overhead, because the outside or any building you're in is going to basically act like a big acoustic box or something like an airplane. Zombies, same thing as a player. The zombie's groaning and moaning comes from the zombie's mouth, which would be right here. And zombie walking sounds would have to come from the zombie's feet. It also makes sense, but something to be aware of when you're designing these particular experiences.
Great. Well, thanks, Adam.
You know, actually, can I show one more thing?
Oh, yeah, go for
I know you're going to talk about profiling and performance, but this is a pretty good graph that shows you immediately what happens with performance and audio. Let's go ahead and get my mouse up here. Scroll down to audio. This graph right here, this is my total audio CPU percentage. So let's go ahead and unpause this. Just watch the graph, and let me shut off spatialized audio. Turn it on, turn it off. There's a hit for spatialized audio. In this case, it's pretty minimal, but it is one thing to be aware of, and using the profiler built in Unity, you can actually see the audio CPU percentage that your experience is currently taking up.
Perfect. Thanks, Adam. So let's talk about some tips while Adam is trying to get ready for his next demo. One of the things that is important for our spatialization technology is to make sure that all spatialized audio is mono. We also want to make sure you target 48 kilohertz audio, because in the pipelines, it will actually be converted to 48 kilohertz. Audiograph itself will actually throw an error at this point if you do not use 48 kilohertz audio. What Adam and I learned is that when you get graphs from designers, they're not always at scale, at real-life scale.
Usually not at scale.
Or usually, yes. And the thing, what is really important with spatializing sound is understanding that the spatialization technology we use assumes the units to be in meters, and so 1 unit equals 1 meter. So when that world scale is off, spatialization sound and the distance curves and such will also be off a little bit. Adam also touched on HRTF performance. So it is important to note that since we're Windows, we run on many, many different devices. And different devices will support different amounts of supported voices. Now, it's also important to realize that you will budget for spatial audio. If it's 5%, you'll have less spatial voices than you have 10%. But again, the 10% on a less powerful device might result in less voices. So it is important for you to keep that in mind when you're designing your application. Below, I have listed some common techniques on how you can deal with devices that are less powerful. So if you have a graph, the first graph on the left that has two emitters, two spatial objects on it, and you need less or you have less spatial audio capability, what you could do is take the emitters off those two individual nodes and submix the sound and basically co-locating them by adding another emitter to it. So you would do that when sounds are really close in distance and are traveling at a similar velocity. One of the other things you can do is put a priority on the spatial objects you have, and if your spatial object count is not high enough, or what you can render, you might drop one of the emitters on one of the input nodes. What's important to notice is that spatial audio is a simulation. So as Adam mentioned before, you expect and you need sounds to come from the right location as you're creating your sound. That means footsteps. You want to put an emitter that actually target the footsteps at the bottom, because that's really what you're used to and that's where the sound is coming from. Same goes for when somebody is speaking. You want to actually put a speaker or an emitter where their head is. Another important thing to note is that vertical location matters. So what I mean by that is that as you now have a high channel, it's important to understand how well that works at certain degrees. So anything above 30 degrees works well. So if I'm looking at Adam and Adam's speaking at me, that almost works well for me. But an airplane flying over or speakers or such are really good to locate because of that fact. The next thing Adam mentioned was the importance of room models and the good use of room models. When you're spatializing sound, you need to use room models to really represent the room you're in, because they will give you the correct distance cues and such. And so don't use them as an effect, but use them to really model the room. Something you might have experienced here is that expectation outweighs simulation. So rain always comes from above, so immediately your brain thinks that the rain really is coming from above. In the next demo, if you hear an eagle fly over, you will naturally be able to localize that sound better, because eagles oftentimes fly over your head, unless you're in trouble. And real-world sounds are more effective for the same reason. Sounds that you know and sounds that are always in a similar location, you'll be able to place them better in those locations. When you're normalizing a sound for spatial audio, it's important to think about normalizing the sound as if it was recorded 1 meter away from you. And as such, the spatialization effect will work really great. You do not need to add any additional distance attenuation, so the spatialization technology with Penrose will take care of that for you. If you have a sound in your UI, for example, HoloLens, that is really important, you can add dynamic compression to make sure that that sound sounds louder when it's really important. All right, with that being said, let's move on to our next demo.
My favorite demo. Well, the other one's good too. They're different. Zombies and dungeons. You can kind of see a theme here. This next demo that we worked with another partner, Silicon Storm, and this is going to be using the HTC Vive, one of the various capable VR headsets that are on the market that actually can integrate quite easily with our audio runtime. And so on this one, this is a headset. I have stage track that's going to be set up, but there's one thing I want to show you inside of the experience first, and then we'll actually do a quick run through on here. All right, let me set these on the floor just to make sure that these are ready. And I'm back. So we can see this level that we've got laid out here. And we're going to start out on this far edge of the cliff here There's going to be wind. So take a moment to really appreciate and listen to the sounds and try to understand where they're coming from. Imagine yourself on the edge there. I'm going to be immersed, so I'm going to be in a slightly different place than you guys. But when you go up the side here, we're going to hear wind. Think of it, you're going up the side of a cliff, and the sound of wind is going to be different. So we've taken time to add different things to these locations. Now, the spatialization settings we can set manually. We showed little bits of code that we can use to essentially talk with the spatializer plugin. And we can simply do basic things. The set spatializer float demos that we looked at before. Set spatializer float. In this particular case, we're just setting this to be a room of none. In other words, we are outdoors. We're not in a small room. We're not in a conference-shaped room. We're not in kind of a supermarket. We're outside, so it needs to change how it's going to do the processing there. All right, let's go ahead and run this demo. Let me maximize this. Find my right controller here. Hopefully I don't fall off the stage. And as it figures, my headset's not tracking. There we go. I'm going to restart this real quick. For some reason, my headset's not tracking here. Let me just move back so I can see me. The way that this headset actually works is we have sensors that are set up on the stage here. And so this gives me the kind of a realistic tracking throughout my environment. And of course, it's not tracking me in my environment. There we go. All right, now we're in. Now take a moment. We have eagles that are flying up overhead there. We have these sounds around us. We have flags that are flapping. You can hear the wind. We've kind of got that edge over there. I'm going to violate a little principle of VR and fast, essentially move myself through this world using this little waypoint system. Now automatically notice, where's Steven? Are you over there, Steven?
Yes.
We can hear the edge of this wind zone here. We're at the very edge of it. Let's go into it. All right, so hopefully you felt a little bit of that chill that was kind of on the edge there. Now we're coming up to our dungeon here. Steven, you want to bring me up to that spot there? Next one. All right, let's go into, we go into our area. Our flags shut off outside. Our eagles shut off outside, so we need to make sure that we don't hear those sounds anymore. As soon as we've entered in this region, we shut those sounds off. Now we have torches burning on the side. Let's move through this area. Again, we can literally hear the fire burning on the sides. And in the dungeon, we have a couple different traps. There's a slight creaking going on of the lumber that's kind of holding the entire place up here, or helping to hold the place up. And I can see there's a trap right there up on top. So let's check out what that guy's about.
Up. Stop tracking.
Right when the trap drops, it stops tracking. Did you see it or no?
Yeah, you did.
You saw it? Because the other thing that we can do, you said you were able to see the trap drop on there? All right. There's one other thing that I'll show you, and we don't actually have to have a headset on. The cool thing about technology nowadays is we can pretty easily switch back and forth between what we're doing with a headset and what we're going to do without a headset. So over this trap on the right-hand side here, there's a lava pits that we pass by. One more track. So arrows that have audio sources on them so we can hear them as they fly by. And then if you notice, they hit the back wall. Hopefully you heard it somewhat behind you, because those hit the back wall and they made a sound at that location when they hit. So the spatialization aspect, I hope you can hear it brings to life. Now with headphones on, it's kind of even times 10, but hopefully with the side speakers here, you got kind of an idea of where those sounds were coming from.
Yeah, great. Thanks for the demo, Adam. So let's switch to the deck again. All right, so that's the end of our presentation. I hope you've seen a couple of great demos that demonstrate how you can add spatial audio to games, but also how you can add spatial audio to your applications in UWP using the AudioGraph API. We can't wait to really see what kind of spatial audio experiences you create, and you can reach out both to me and Adam afterwards we'll help you out with building those experiences. You can also watch the separate recorded presentation on the spatial sphere on channel 9, and we will post code samples for a lot of the demos you've seen here today on GitHub, and we'll also post the games for which we can always share the full resources, but we'll put those online as well. We'll post a link to both of them on our channel 9 video page. All right, well, thank you for your time today. I hope you had a great time, and I hope you're ready to build some spatial audio experiences.
Thank you all very much. And for the folks in the room, we're going to stay a little bit after, so I'll be here to answer questions. And if you want to check out the headset, check anything with that, come on up and talk to us too. Thank you all very much. Enjoy the rest of the build.
Thanks a lot.